Hello everyone, welcome to the session on data science interview question. So before starting with the interview question, I would like to introduce myself. So my name is Ankur Chaudhary. I have around 4 years of experience in data science. Currently, I'm working as a senior data scientist for multiple financial company domains like Morgan Stanley, Wells Fargo, and other US financial companies. So in this session, we are going to cover frequently asked interview questions on data science in various industries with multiple domains like in the financial domains, in the health sector domain, and other industries also. So let's start with the very first question. So now what is data science? This is the very buzzing word today as a career. Everyone wants to like acquire the skills of a data scientist, to work as a machine learning engineer, to work as a data analyst, to work as a business analyst in multiple domains. So we should know about like what exactly this term means. So it is a field which is making a very huge impact in our fundamental ideas, and the main thing about data science is like we are extracting the key insights of the data. So every day we are collecting the data in millions, right? Whenever we surf on internet, we are trying to gather as much as data from about our need. So for example, we are texting to somebody, so that is also the data we are recording from both the sides. For example, if you are searching some product on Amazon or on Flipkart, that is also the type of the data which is being collected by the servers of these particular companies. So every industry is recording the data in millions, and on top of that data, data scientists are analyzing on the basis of the features, on the basis of the use cases given by the business team to improvise their productivity in their environment. And at the end of 2022, not just 7 lakh, it's more than that. These openings are going to be available for the data scientists, for the data developers, and for the data engineers. Now, a term data is being included with the scientist term also, with the data developers also, and with the engineers also. But their roles are slightly different, but yes, they have to come up on the common data at the end of the day. So data scientist is responsible to analyze the data from the historical and to make some predictive patterns for the company. For the data developers, now data scientists need some data to analyze, right? So from the primary sources, from the secondary resources, all the SQL query developers and the data engineers, they try to massage the data, they try to make the data which is used for the machine learning purposes. So there are a lot of terms which some people might get confused, like what is a data scientist role and what is a senior business analyst role. What do you mean by machine learning engineer? So all these terms we are going to discuss it today, so that you can apply at the right time and the right type of job in future. Now, as a career in a data science, the satisfactory part is like you are going to get the fulfilling work. So you will be getting the interesting technical topics. So for example, today in expressways, today you we are able to compute the velocity of a car. So whenever car moves through a sensor of a like to compute the speed of the car, we can get the speed by just detecting from the sensor. So that is also an AI technique. We also have the classification, so classification of images, the classification of objects, the classification of running object. So that is again an interesting topic. In today in text processing also, we have a lot of AI engines, like we have Alexa, we have Google, we have Siri. So these are the interesting technical topics where we can easily deep dive to explore more. And yes, it's in high demand. You will also get the great pays and the benefits. So if you're working with Amazon like a company, you will also get the stocks also, apart from a great pay salary. So yeah, it's a really booming career, and there are a lot of things to make sure to work in this domain, because it's not just a one single thing. So it's a interdisciplinary. So it's not just like a mathematics and statistics. So if you in from this pie chart, you can see mathematics and statistics has a combination with computer science, which is going to give you a machine learning job. Okay, mathematics and statistics with the domain knowledge. So I'll give you a short example on that. So for example, if you're working in a health sector, and in a healthcare sector, definitely you're going to deal with the data, with the biometrics data, with the BMP data, That means all these type of variables you need to understand. Now I'm using some terms like variables. So whenever I say about anything data and variables, that means, and that too a domain specific data. So the meaning of domain specific, that means the data can be from the healthcare sector, it can be from the finance sector, or it can be from some other sectors. So I'm taking example for the healthcare sector. So healthcare sector can have multiple features. So what could be the understanding of the features like blood pressure? Blood pressure is one of the feature, right? Whenever we compute the blood pressure for any patient, whenever we are going to compute the sugar level, so that is also one of the feature. So data is combination of such type of features. We have insurance also as one of the domain today. So insurance, like whether we are claiming the insurance or not. So this is also a feature. Now feature can be of continuous or of categorical type. So continuous and categorical basically means, so if it is a categorical variable, that means it consists of a categories, right? So whether a person is claiming the insurance or not. So if it is claiming the insurance, yes. If it is not claiming the insurance, then it's no. So basically, claim variable is the categorical variable. What if I have some variable called average? Now average is a number, right? So we have 59 value, we have 60 value, we have 65 value. So this is not categorical at all. This is a continuous variable. So here is the difference between continuous variable and a categorical variable. In continuous variable, the values keeps on changing. So these are some of the questions which an interviewer is going to ask in between the other questions. Like whenever you are analyzing on some data, are you comfortable about the continuous data, or are you comfortable about the categorical data? Okay. So now coming back to the question. So mathematics and statistics, yes, it is required at a higher extent. So mathematics, we have linear algebra, we have probability, we have statistics, and we have calculus. Okay, so that is the combination that we have studied till our 12th standard level. But yes, today because lot of SSD algorithms, now I'm using the term called SSD. So SSD means state of art algorithm, or you can say some algorithm which are pre-trained on some data, right? So that needs a lot of understanding of calculus, lot of understanding of probability, lot of understanding of statistics. That is not just limited to the intermediate level. So we need to deep dive into these topics as well to get the better understanding of any upcoming machine learning algorithm in AI domain. And also domain knowledge is very important, which I just told you about the healthcare sector. Like if I'm working on the insurance domain, I should know when a person should claim the insurance. If I'm working in the healthcare domain, I should know what that blood sugar level variable exactly means. I should know if I'm working in the finance domain, like what should be the CIBIL score to allocate a loan to that particular person. So all these understanding for each domain is required to work in a data science field. So we cannot just openly take the data and apply some machine learning algorithm on top of that and can do some predictions. It's very important to understand the objective, and objective can easily be understood once you have the data dictionary of the data to you. The term data dictionary is also very important here. So when I'm saying data dictionary, and it's your right to ask your team that can you provide the data dictionary to work on a specific data. Because if you are meeting somebody's objectives or use cases, you can't just go and gather the data from the primary resources. You just need to understand the data from top to bottom and from left to right. Like what type of data you are dealing with, what type of data you are going to collect from the multiple resources, and you should also interact with other team members, like with your data engineers who are going to gather data from the multiple sources and massage it and give it as a one form of data to you. As a data scientist, you're going to work on data frames. So data frames is nothing but just a tabular structure data. That means a data which is consist of rows and columns. So that is a data frame. In pandas, or I'll say in Python, we can work on pandas to work on data frames. Okay. But I won't be guaranteeing you that every time you're going to get the data in a tabular structure. Sometimes you also have to do some extra efforts to get the data in this form, because whenever you do the web scraping, so web scraping is another term. Web scraping is the another term where you scrap the data openly from the website. So it is not going to be gathered in the form of a tabular structure. You have to do some pre-processing, or I will say EDA, exploratory data analysis, on top of that data to make it analyzable. And the third part is here you can see software engineering and some traditional research. So mathematics with domain knowledge will give you the traditional research of the data by applying some quantitative techniques. Adding to the computer science, that means we also need some programming languages like Python, like R. We have some latest technologies coming up like Neo4j to work on the graph data. And the combination, that means the most common section, a person who is having the computer science knowledge, that means any command on a programming language like Python, having a good command over the mathematics and statistics part, and have a clear knowledge about the data, that means a domain specific data, that particular person would be called as a data scientist. Okay. Before that, we have machine learning engineers. So machine learning engineers may not have that domain knowledge in their mind, but yes, they have a very good command on the programming language along with the mathematics and statistics. So a clear example for the machine learning engineer, as I have also worked as a machine learning engineer, so I would say, like if I'm given a data in a tabular structure and I have three columns A, B, C with some set of rows, then as a machine learning engineer, what type of insights I can get from this data? So I can apply some descriptive statistics that we will be discussing later on this presentation. So descriptive statistics for me would be, what is the average of this column? What is the average for this column as well? And what is the average for this column as well? If they are continuous data. As I told you, continuous data is a numeric data. So I can compute mean on top of that. I can compute median on top of that. I can compute mode as well. So if you might have heard these terms in your intermediate level, but no, it is not just limited to these terms only. You can also compute variance. You can also compute standard deviation. So these are some statistical terms which are used to see like how much your data is showing a variation, or what is the average of your data at a particular point, or what is the mean value of the data. That means median is nothing but just a middle value of the data. So middle value means, so if I am having a number line, so what is the middle value? That is 5. So 5 is the median L, which divides your data into two parts. That should be 50-50%. So that is the median value for me. Okay. So this is just the small snapshot of like what type of statistics we do. Apart from descriptive statistics, we also use one term called inferential statistics. Inferential statistics. So inferential statistics is again whenever we type to study the type of a distribution, like how my data is distributed completely. So there are multiple types of distributions, like we have normal distribution, we have skewed distribution towards the left and towards the right side. So these are some knowledge that a data scientist or a machine learning engineer should have to work on a tabular structure data. And yes, these are the technical tools, like I just told you, Java, SQL. So SQL is used to gather the data from the either from the relational databases, or if you're using some other databases, then you should have that expertise to compute or to gather the data open sourcely, like fetching from or web scraping from the websites. We have Python. So Python today is having a good version like 3.6, 3.8, 3.9 as well. We have R. So R is again a very good tool in terms of statistical libraries. So that is one of the best framework to work on the statistical data. I would say in the health domain sector, we have R also. We have SAS also, which are loaded with some good libraries. In Python, we have scikit-learn as one of the package to work on the machine learning algorithms. We have pandas, that is also one of the best library to work on the data frames. And we have numpy. Numpy is nothing but just if we are computing a numerical calculation on top of the numerical data. So we have matrix multiplication, we have transpose of the matrix, right? So that type of computation, we have some functions inbuilt inside the numpy library which we can use inside Python. We have caret in R, we have machine learning library in Spark as well. So if you're working in the on the Spark engine, you can always import this library to work on Spark programming language. So Spark with Python becomes PySpark. Spark with Python becomes PySpark. Okay, we have huge level of software tools like H2O.ai, we have Data IQ, we have Skuro, we have AWS ML services. And if you're deploying your services as a one package, we have Docker. And for any visualization, we can have Tableau. So it's not compulsory to have the knowledge of all these tools. Let me make it very short to you. You don't need to go through each and every software. If you're having command, because today data IQ is the most common tool used by almost every industry. Because in the data IQ, we have a good flow of the charts, flow charts of your projects in Skuro, which is also completely based on the text processing. And yeah, if you're working on a cloud services, we have AWS, we have GCP, we have Azure, and they are pretty loaded with the machine learning API services, which you can use by just putting your data inside. And we have Docker to, if you are making your application at a production level, we can use Docker. And yes, if you're working as a storyteller to your business team, then you can use Tableau. And yes, this is the theoretical knowledge, basic mathematics, and some additional mathematics topics like Bayesian statistics, A/B testing are some of the topics which you need to deep dive whenever a requirement is there in your use case. Okay, so yeah, I would talk about the huge level software tools like we have Data IQ. So Data IQ is one of the best tool today. We have H2O.ai. So these are some of the tools which companies are using at a production level. So Data IQ is mostly famous for flow charts. So flow charts for any computation. So let's say I'm having a data set A. I applied some statistics. I applied some statistics like mean, for example. So I am now getting a data set B. So this type of flowchart I can easily get in Data IQ. Now on top of that, I applied some machine learning algorithm. Okay, let's say I applied some supervised machine learning algorithm. So I would be given some APIs. So APIs as nothing but just application programming interface for any particular package. So machine learning is one of the package inside Data IQ. So you would be getting those APIs, and let's say I am using supervised algorithm, and that supervised algorithm is giving you the results. So that type of flow I can easily see in Data IQ. So we have, I think, around 15 to 20 days trial in Data IQ also. So you can just also go and create your accounts and you can explore the open source services in S2 in Data IQ. Similarly, we have for H2O.ai, and we have another tool also called Skuro. If you are like a data lover for mostly for the text data, for the text data. So text data is nothing but like whenever I'm reviewing a product on Amazon or on any other services who are selling the products online. So definitely I have to give my sentiments like how is the product, and is it giving me some problem like that. So if I'm writing it's a good product, it's a good product. So that means this is a positive sentiment, right? This is a positive sentiment. Or if I'm writing product is not good at all, product is not good at all, that means I'm not satisfied with this product. So this is a negative sentiment for me. So a collection of the text data, so I would say a corpus of text, a corpus of text data is analyzed under the technology called NLP, which is a natural language processing today. Okay, so we have some tools built on the NLP technology, the niche technology, I would say, which is a skewer tool for us. So again, depending on the objective you're working in your company, you can always go for these tools if they are allowing you to do work upon. We have machine learning knowledge also, like as one of the most primary knowledge to work as a machine learning engineer. So we have multiple algorithms in machine learning. So we have supervised, unsupervised, NLP, bias and trade off, gradient descent, some regularization techniques, some bagging and boosting techniques. So a quick overview of supervised and unsupervised. So this is your machine learning. We have supervised, we have unsupervised. So in supervised, that means I know the target variable. I will explain what is the target variable here. In unsupervised, I don't know the target variable. It is not there. So in a supervised machine learning, we are well aware about the historical data. Historical data. For example, if I would say in 2021, what was the sale for my air conditioner in from, let's say, from July to August, from July to August. So if I gather the data from July to August for these 2 months, I would have the revenue, right? I would have the revenue recorded in my system, right? So that is my target variable. That is my target variable. Now, when machine learning jumps into such scenarios, because now today it is 2022, okay, and July and August are still yet to come, these months. So if I want to increase the revenue for my air conditioners, so what type of marketing campaign, or how should the price of the AC needs to be showcased on the online platform? So these are some of the factors which can impact your revenue positively also, negatively also. So machine learning helps you out. Like, what are the most important factors? What are the most important factors whenever you apply a supervised machine learning algorithm to make your productivity more efficient? But when it comes to unsupervised algorithms, that means you need to find out the target variable. Obviously, you have some idea by reading the objectives, right? That means the use cases. Once you understand the use case, like I want to see, so let's say I'm having Amazon here, right, and I'm listing some products here, but I want to see what makes these products more sellable, right? Is it the number of the clicks? Is it the number of clicks? Or is it the time is spent on the website, or time is spent on the application? So I'm not sure, right? So like which variable or which factor is more compliant, or having more relation with the productivity or the product selling of those products on these services, right? So for resolving such type of problem, we have unsupervised algorithm like clustering algorithm. We have clustering algorithms like k-means clustering is there. We have a hierarchical clustering also to resolve such issues. So that was a quick snapshot about the algorithm. So I won't be able to explain the complete theory about, because it's quite like a big topics. For that, you always need to spend some more time. But yes, in interview they might ask you like what is the exact difference between supervised and unsupervised. Okay. Now, they might also ask you the very famous question, that is bias and variance trade-off, that we will be discussing in the further questions. We have gradient descent also. We have some regularization. So regularization is having a direct connection with bias and variance, and some bagging boosting techniques if you're working on random forest. So another question is, what do you mean by event and sample space? So yes, as I told you, you should have understanding of basic mathematics like statistics and probability. So I will take a short example here. So if I'm tossing a coin twice, so I am having a coin which can have only two possible outcomes, either head or either tail. Okay. Now I'm tossing a coin twice. Okay, that means two times. So what are the possible outcomes I would be getting? So let's say I toss the coin twice. So first outcome, let's say I got head on both sides. Okay, because there are two coins. Let's say in the second, head tail. In the third, let's say I'm having tail head and tail tail. So the set of the observations which I got after applying the experiment. What was the experiment? I'm tossing the coin twice. Okay. After experiment, I read some observation. So in the first observation, I got two heads. I got one head and one tail on their respective coins. I have tail head and I have tail tail. So this is called a sample space. This is called sample space for me. Okay. Now, on top of that, I want to compute a probability. Okay. So probability is computed on an event, because the definition says itself. When you compute the probability for a particular event, you need to get the sample space first. Okay. It gives you the likely or the likeliable outcome for that particular event, that how much probabilistic this event can occur next time, right? So from the question itself, you can see, uh, let's say any subset E for the sample space is known as an event. So if I want to compute the probability, if I'm tossing the coin twice, what is the probability of getting at least one head? Okay, at least one head. Now you can see at least one head and just one head. There's a difference. At least one head and one head. So here you can see one head, here it is, right? So what is the probability of getting head when I'm experimenting this particular event? So it is total, like I am having two outcomes, so 2 divided by the total number of outcomes, that is 4. So that is 2 by 4. That means uh, 0.5. So 50% is the probability that you will see head whenever you are tossing a coin twice. Okay, so that is an event. That is the probability of the event. Now, how to say this? That means, because you should also try to explain the results to your team as well. So 50% is the probability I will be getting one head whenever I'm tossing a coin twice in this particular experiment. There are other questions as well where you will have to see probabilities like this also. 0.05. So 0.05 is 5%, and 0.50, this is 50%. Okay, and the summation of all the probability is always computed to 1. It is always computed to 1 here. So that is the difference between your sample space and events. Okay, and these are some formulas for that. So probability always lies between 0 to 1, and the probability of the total event is equals to 1. Or you can also say union, or you can say the summation of the events on which we have computed the probability is also equals to 1. It cannot be more than 1. Another most important question is your conditional probability. Now, under this question, we have some base rules also. So, conditional probability is the probability of an event happening, given that it has some relationship to one or more events. So, for example, we have a parking space, right? We have some parking space everywhere in our cities. So, this is a parking space. This is a parking space. So what is the probability of this parking space? What is the probability of this parking space? Can we compute directly? No, we cannot compute that, because parking space keeps on changing, or it keeps on occupying by some other vehicles by time also, right? Because it is connected with multiple factors, I would say. So it is connected. It is also connected to time of day you park. That is one of the feature, or you can say that is one of the event even, or it is also connected like where you park. So whenever you're computing a probability which is conditional, so it is conditional to the time of day you parked or where you park. So you cannot compute direct probability on the parking space. Okay, and we have the formula for that as well. So if there are two events, or if there is, obviously there will be two events here. So for that we have the formula P of B slash A is equals to P of A intersection B divided by P of A. So that is the conditional probability formula. Okay. On top of this, because it has a direct connection to your Bayes rule, Now, what is a Bayes rule here? It is basically slightly more refined. I would say more refined than conditional probability. Okay, so in a nutshell, it is basically an actual probability, probability of an event given the information about the tests. Okay, that means the event has already occurred. Okay, so P of A divided by B is equals to P of B slash A, P of A divided by P of B. So that is the formula for that. Okay, for the Bayes theorem. In 12th, we have studied about the Bayes theorem, right? It is simply that only, Bayes theorem. Main thing we need to understand about this, like the event has already occurred. Event has already occurred. Whenever you are computing such formulas, you need to understand that event has already occurred, because whenever I am talking about the parking space, like computing the probability for the parking space, it has a direct connection with the time of day you park. That means the time is the event, okay, and the location where you park. So these are the events for me. Considering these events, I can compute the probability of the parking space, right? So we have the observations for time, we have the observation for location. Okay. Another most important question is mutually exclusive events and the independent events. So again, if you have studied about the set theory in your 12th standard, we have some events called independent events. So in independent events, basically from the term itself, the events are independent. So I'm having an event A, I'm having an event B, and there is no connection between these events. So such type of events is called independent events. Okay. Best example I would say, there is a customer. Okay. There's a customer who files an insurance claim today. Who files an insurance claim today. Okay. There's a customer who files an insurance claim today. Then what is the probability of the customer B filing a claim? So there's another customer. Okay. There's another customer and they don't know each other. They don't know each other. Then what is the probability? Can I compute the probability? Of course not. I'm not sure like whether the customer B has also arrived to the company for the claim, right? This customer came to the insurance company for the claim, and this customer came to the insurance company for some other event, right? So such type of scenarios comes under the independent event. Okay, that means P of A intersection B, because there is nothing common between these two events, which is called phi. Okay, which is called phi. Then what is mutually exclusive here? Mutually exclusive events. So again, here I will say if A happens, B cannot happen. B cannot happen. Let me explain you with an example. The mathematical notation for this would be A intersection B is phi. So if I'm rolling a dice, so dice is having 6 outcomes, right? Dice is having 6 outcomes. So 1, 2, here 3, 4, 5, and 6. So the sample space of the dice would be 1, 2, 3, 4, 5, 6. Okay. So there is an event. So can you it's like can you give me the sample space? Like if I'm rolling a dice, what would be the possible numbers which are less than 3? So yeah, so there is a dice. So there is a dice which is a cubical 3D picture. So whenever we are rolling a dice, these possible outcomes arise, right? So if I'm rolling a dice, 1 can come on the top, 2 can also come on the top, 3, 4, 5, and 6 can come on the top. So that is called a sample space. My dice cannot throw any other number apart from these numbers, right? It is the sample space which we just had a discussion in the previous questions. Now there is an event.
I rolled a dice. What is the probability of getting a number less than 3? That means less than 3. And how many numbers are there which are less than 3? Only two numbers. So the sample space for this particular event is 1 comma 2. Okay, let's say I'm having another event. What is the if I rolled a dice, what are the numbers which are more than 4? So we have two numbers for that, either 5 and 6, right? Now if I try to find out a relation between these two events, if I try to find out the relation between event 1 and event 2, is there anything common? Of course not. Both the events are mutually exclusive, but they are from the same sample space. Mutually exclusive, but they are from the sample space. That's why mutually basically tells you that it is coming from the same sample space. So that is your definition here. Okay, so I would say E1 is having no relation with E2, which is called phi. So phi is the term which is a mathematical symbol which says that there is no relationship between these two events. So such type of events are called mutually exclusive events. Okay, but in independent events, event 1 and event 2, they can be completely separately events. There is no relationship, and the sample space is also not common to them. So such type of events are called independent event. So they don't know each other at all. Here at least the numbers are gathered from the universal space or the sample space of the dice. So these are the differences between these two events. So again, you might need to explain the examples also if asked in the interviews. Okay. Another good question is the what is the probability of rolling a total sum of 4 with two dices? Now see, you should always see like you have two dices. You have two dices and whenever you're rolling the dices, the most possible set of outcome could be like in the first roll I would get 1 and 1 on both the dice, in the dice A and in the dice B. In the second roll I would say like it is like this: 1 comma 3, 1 comma 4, 1 comma 5 and 1 comma 6. It says like I rolled dice A and dice B, and in the first six rolls I got 1 in the dice A, and I got 1, 2, 3, 4, 5, 6 like incrementally in the dice B. Okay, similarly I would say 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5 and 2 comma 6. And similarly we have 6 comma 6 sorry 6 comma 1, 6 comma 2, 6 comma 3, 6 comma 4, 6 comma 5 and 6 comma 6. Now what is this? This is a sample space. This is a sample space, right? This is the sample space of the experiment. What was the experiment? Rolling the dice A and B. What would be the observations? These are the observations. Total 36 observations, right? So 6 here and 6 vertically downward. So 6 into 6, 6 into 6 is 36. So total 36 observations I got whenever I rolled dice A and dice B. Now what is the event here? Let's read about the event. What is the probability of rolling a total sum of 4 with two dices? So I need to see. So if I consider this example, let me change the color here. If I consider this example, so this says I got 1 on dice A, and here I got 1 on dice B. Is it making a sum of 4? No, because 1 plus 1 is 2, right? So I have to find the pair in this 36 observations. In this 36 observation, I have to find the pair which makes a total of 4, right? So I would say this 1 comma 3, that means 1 on A and 3 on B. And I would say this also 2 on A and 2 on B. And we have because we have 1 comma 3, then we can have 3 comma 1 also. We have 2 comma 2 also, right? So we have total how many? We have total 3. Okay, so total total events which are having the sum of 4 after rolling the dice A and dice B is total 3. Okay. And the total number of observation is 36. So 1 by 12. And then you can compute it. It will come in some zeros, right? So that is the total probability. So let me do it in front of you because we need to understand from all the sides. So 12 8 is 96, and so I would say 0.08. That means 8% chances are there whenever you roll a dice A and dice B, you will see the events which are making a sum of 4. Okay. So that is how you answer a probability question. Okay. Another question is, what do you mean by sample mean and variance? Now I would say sample mean and sample variance. So in a nutshell, the sample mean and sample variance of a random sample. So random sample here means so we have the population data set. Okay, we have a data set called population, for example. Okay, now I cannot directly analyze on top of population only every time. I have to fetch some samples from this population to make my research more closer to the population only, because population data keeps on changing every day, right? So I fetch some sample 1, sample 2, sample 3, and sample 4. So the basic idea of having sample mean and sample variance is uh, the sample 1, sample 2, sample 3, sample 4 I fetched from this population data. If I compute the mean on top of, so n is the total number of the data points in my population. Okay, this is your mean formula. So if I compute the mean of sample 1, sample 2, sample 3, sample 4, and take the average mean of these four sample mean also, it should always have a similar number of population mean as well. I would explain again and again. So I take the sample mean S1, that is your mu1. Okay, so your mu1. So in case of one sample out from this population, this sample one mean should always be closer to the population mean. Otherwise, see, in most of the cases, it will be always similar to the population mean. But sometimes we have some terms called bias, or maybe the sampling I have done is not that good sampling, because we have different type of sampling. We have strata sampling also. So strata sampling nothing but just a group sampling. So I would say like strata, you can say like 10 data points in one strata. Okay. So if I'm closing my eyes and I pick some data points from this population, I would gather only 10 points. So that is the strata sampling. Random sampling, just taking the sample out from this population. Okay. So the ideally, whenever you take the average of this population, or whenever you compute the mean on the population data set, let's say this is mu p. So the mean of the samples which you have extracted from population should always be similar to the population mean. Otherwise, it's not a good sampling you have done. Okay, so that is the sample mean here, and the same thing goes for the variance as well. Okay, because the variation which population data is showing, the same variation I should expect from the sample also, right? So the variation which population is having, let's say some 2.6 is the variation value, then that similar value of variation I should see in these samples also, because at the end the samples are extracted from population also. It should show the same behavior to me. Otherwise, again, it is a question on the sampling. So that type of understanding we have to keep in our mind. Okay, that type of understanding, because see, this is the classroom and these are the students which represent this classroom. So at the end also, if I'm taking one student out from this class, and I and now this is the representative, or you can say representative of this particular classroom. So already I know what is the classroom here, and I've taken some sample out from this. Now this is the sample. This is the sample who is going to represent this population or classroom for me. Okay, so it should have the same metrics. It should have the same metrics which my population or which my classroom is having. Okay, that's why we always compute our metrics, our machine learning algorithms we run on the sample data set, not on the population data set, because you cannot analyze your population data at one go. It keeps on changing every day. Your population data set site keeps on changing. So right now at 12:43, we don't know like how many children got born, and at 12:44 how many children like born, or like how many accidents happened. So this is the data which just keeps on changing. Okay, that's why we fetch some samples from this one, and we have the formulas for the same. Now, what is the Chebyshev inequality? So Chebyshev inequality is the another you can say the most important event to find out the results in our data set. So I would say in a way like can you tell me the results or can you give me the let's say the percentage of data points percentage of data points in like in some you can say distance metrics I would say, or I would say like using the combination of mean and standard deviation, because these are distances only at the end. Standard deviation. So Chebyshev inequality results basically we use in our analysis whenever we compute the descriptive statistics or inferential statistics to find out the 75% of the data set. We basically use the term called Chebyshev, and it has some results like mu minus 2 standard deviation and mu plus 2 standard deviation. So mu is the average or mean, and sigma is the standard deviation. So basically, there are results of Chebyshev like 75%. Another important point to be asked in interview: 75% of data points, or you will say 75% of the data set, always lies between mu minus 2 standard deviation, mu minus 2 standard deviation to mu plus 2 standard deviation. Okay, it's a little intervals concept, like we have interval mu minus 2 sigma, mu plus 2 sigma. In mathematics, these open interval says any value any value which belongs, let's say I'm having a variable called x, and x belongs to this interval. So x can have the value between these two extreme points only, not more than that. Okay, so Chebyshev's inequality says that 75% of the data points always lies between these two intervals. Similarly, another result: what if we have 3 standard deviation? That means mu minus 3 standard deviation to mu plus 3 standard deviation. So if there is a variable called y and it belongs to this particular interval, it says 89% of the data points always lies between mu minus 3 standard deviation to mu plus 3 standard deviation. Okay, you might be thinking, what is standard deviation here? What exactly? So a pictorial graph for this one is this one. So basically, this is a normal distribution curve or a bell-shaped curve for me, and the intervals here are set something like this. So this is your mu, this is your mu plus 1 standard deviation, mu plus 2 standard deviation, and mu plus 3 standard deviation. Similarly, mu minus 1 standard deviation, mu minus 2 standard deviation, and mu minus 3 standard deviation. So answering from the statistical point of view, I'm just saying that this data point is this much distance from the mean value. This is basically your mean value here, mean value of your data set. So I'm having a variable called, let's say, salary. Okay, I want to see the distribution of this salary column. Okay, I got the bell-shaped curve. Now I want to see the data points under 1 standard deviation, under 2 standard deviation, and under 3 standard deviation. Who will give me this answer? Chebyshev inequality will give me this answer after computing this formula. Okay, so we do not directly use this formula, we just use the results of Chebyshev inequality. That's why it is important to remember the results. Okay, so you can say mu and sigma we have, and 1 upon k square. So k square is again the constant. This is called the constant value here. So that is your Chebyshev inequality. And yes, this is I was talking about the descriptive statistics. So in descriptive statistics, we talk about these terms only: calculating the mean, calculating the median, calculating the center and location of the data. So if I'm dealing with the data having coordinates, so if I'm dealing with the geospatial data, I would say the term geospatial data. Okay, so geospatial data consists of the data, basically your demographic details, or you will say geographic details. Okay, so if you're working with the companies who are dealing with the geospatial data, definitely you will encounter with these types of data. So demographic details of a customer and geographic details of a customer, like the coordinates, longitude, latitude. Okay, so some basic examples of such type of data. Demographic data of a customer, I would say the location of the customer, city in which the customer is residing, the state of the customer, or the pin code of the customer. Okay, so these are some of the factors, or you will say features features for demographic data and features for the geographic data. We have quartiles. So quartiles basically is also computed. So you should always remember the normal distribution curve in your mind to see like where the quartiles happens. So again, this is your mean value, this is your mu. Okay, and this is your 1 standard deviation, mu plus 1 standard deviation, mu plus 2 standard deviation, mu plus 3 standard deviation, and similarly mu minus 1 standard deviation, mu minus 2 standard deviation, and mu minus 3 standard deviation. Okay, and we have a mean, we have median computed on top of this only. We have variation, we have range. So range is what? This is your minimum value. Okay, and this is your maximum value. And we have interquartile range. So IQR we have. So interquartile range is basically computed between the quarters. Okay, so like this. So I would say this is the first quarter. So it is a difference with of a 25%. So let's say 25%. So 12.5% here, 12.5% here, and then this is totally 50%, 25% here, 25% here, and then you can take a difference, because on the left side this is 50%, and on the right side this is 50%. Okay, because in the normal distribution, let me tell you the definition of a normal distribution here. When mean value is equals to median value is equals to mode value. So for me, if this is the variable called salary, and if I calculated the mean value of salary, and if I calculated the median value of salary, and if I calculated the mode value of salary, and if all these values are equal, that means it is a normal distribution curve. That means the salary is distributed normally. So once I get to know that this is a normal distribution curve, which we denote by capital N, we can easily compute IQR. We can easily compute the minimum value, that means the minimum salary, maximum value, that means the maximum salary, and then the interquartile range. That means what are the total salary points under one quarter? What is the salary point under the 50%, which is the most bulgiest part? This is the bell-shaped curve here. Okay, which we always focus upon. This part contains the maximum number of the data points. 50% of the data set is stored under this only. Okay, and then we have some data points here and some data points here. We have then variance and the standard deviation. So you should always remember what is standard deviation, why we are doing this. Okay, so sometimes you have to tell the result like this data point is one standard deviation away from the mean, away from the mean. That means you are telling this explanation that the point which is lying here is a one standard deviation, because the distance between these 2 points is one standard deviation. Okay, now if you're saying there is a point here, how can you explain that this data point is two standard deviation away from the mean? This is the mean value. This is the mean value. So one standard deviation plus one standard deviation, that becomes a two standard deviation. So standard deviation is nothing but just a distance only. It's your distance. It's your distance only. So these are some of the descriptive statistics we always perform in Python, and in R. We have the direct functions for that. Okay, either like dot sum b. If you run this function, all the statistics you are able to see here will be computed along with the interquartile range, mean value, mode value. Okay, everything will be computed in R and Python both. In R and Python both, we have the functions for that. So you don't need to compute separately for each metric. There's a direct function. And in Python we have describe describe the function. In R, this is in R, this is in Python. Okay. Okay, another question is what is correlation and covariance? So from the definition, very easy to understand. So covariance and correlation are two mathematical concepts. So if you have studied in your statistical subjects, these are the terms which are highly like asked also in the distributions. Whenever we are computing the relationship between the features, these terms definitely will encounter. So these two approaches are widely used in statistics. So both correlation and covariance establish the relationship. So in a nutshell, whenever you are analyzing the relationship, whenever you are analyzing the relationship between two variables, between two variables, or more than two variables, more than two variables, then correlation jumps into the picture. Okay, you're trying to find out that, let's say x1 is one variable, x2 is another variable, how much x1 is correlated to x2, or I will say how much x2 is correlated to x1. Okay, so the best example is like if you are selling an ice cream. Okay, so ice cream can have a direct so ice cream revenue can have a direct relation with the temperature, right? If the temperature goes up, then ideally I would say my revenue should also go up, right? Because people will buy more ice cream, my revenue will also increase. So temperature is one of the variable, let's say x1, and revenue is one of the variable called x2. Okay, so to find out the relationship between such variables, correlation and covariance comes into the picture. Okay, if the temperature goes down, if the temperature goes down, how it will impact my revenue? I can't say without the data, right? Ideally I will say like maybe people like more ice cream when the temperature goes down, because we don't know, like we don't know our data, how like what type of data I'm dealing with. Okay, so you should always answer the question once you are familiar with the data. Okay, once you are familiar with the data. So without understanding the data, you can't answer the question directly. So this is the pictorial graph for the covariance and the correlation. So this is the negative covariance, this is a zero covariance, and this is the positive covariance. So again the example is, let's say the temperature goes down, so my revenue may decrease. In this case this is a neutral case. Okay, I'm not able to find out the relationship between x1 and x2. Okay, not in the example of temperature and revenue. There can be some other examples like I'm not able to find out the relationship between the variables which have like let's say x1 x1 and x2. There are some variables and their data points are not common at all. Okay, they are not showing any kind of relationship. So that relationship will be a zero correlation. Okay, that means they are not correlated at all. What if I'm having a relationship like this? So what if I'm having a relationship like that? Means this is an increasing relationship, right? This is an increasing relationship. That means if this is x1 and this is x2, so on increasing the x2, so I'm standing here, I'm moving closer to, or I'm increasing the value 1 2 3 4 5 6. Okay, and here also we have 1, we have 2, we have 3, we have 4, and there is one guy which is standing here as well. So x2, like on increasing the x2 value, your x1 is also increasing, right? So that is a positive correlation. That is a positive correlation. Okay, and if it is like this, if it is like this, again I'm standing here and I'm moving towards x1, sorry, x2, and this is x1, and here it is coming towards the 0 point. Okay, so on increasing the x2, my x1 is decreasing. So this is a negative correlation. This is a negative correlation. For now you can understand here the temperature, as well as the temperature is increasing, my revenue is also shooting up. Here you can say my temperature is decreasing, so my revenue is getting down. Okay, temperature, my revenue is getting down. So this is a negative correlation. Okay, so uh, covariance is also like the same concept. Another thing I want to confirm here with the correlation is we have Spearman rank correlation also. Spearman rank correlation, rank correlation, and we have Pearson correlation also. Pearson correlation. Now you might be thinking why, where we are using these concepts. Okay, so in linear regression, which is one of the supervised machine learning algorithm. Okay, in linear regression we always try to find out a relationship, okay, which is a increasing relationship, that linear regression objectives. Okay, so whenever we are running this such type of algorithms, we need to see like whether the variables x1, whether the variable x2 are showing the positive correlation or not. If they are not showing, that means either there are some values like outliers is there, or x2 is not like is not belonging to the use case which we are using, or we have to discard this variable from our computation. Okay, because we need a set of the variables which are showing a positive correlation, okay, or some type of relationship which is an increasing relationship. That's why these concepts are important, and that's why we use the Pearson correlation also, Spearman rank correlation also. The objective of using Pearson and Spearman rank is to make my correlation more refined. Okay, to make my correlation more refined, to find out the best variables which are showing some type of relationship together. Okay, that relationship could be a negative relationship, that relationship could be a positive relationship, but there should be some relationship between the variables. Like again the very old example, your year of experience, right? Your year of experience is directly proportional to your salary. Can I say that? I can say that, right? Because on increasing the experience, ideally your salary should also increase, right? So that is a positive correlation. Okay, but you cannot say like a graduate is earning the salary like in crores. See, a graduate can earn, but that is like once in 100. So that could be your outlier, that could be the point, a data point in your data set which you need to focus more, or you may have to cap that value, because whenever you ingest this data point in your algorithm, your model can become biased, because there is only one data point in your data set who is earning in crores. Rest all the graduates are earning in some in a good range. Okay, which is in the market. Okay, so that is all about your correlation and covariance. All right, so we have some distributions in our statistics. So the distributions we have in discrete and in our continuous. So first of all, you should know the difference between a discrete variable and a continuous variable. Discrete variable and continuous variable. So discrete variable, the best example I would say gender. So gender is having, so we have male and we have female, right? Now if I encode this variable, let's say male with 0 and female with 1. So this is a discrete variable for me, which have discrete values. So discrete values are those values which are in the form of a whole number, which are in the form of a whole number. Okay. What if we have the continuous variable? So in continuous variable, let's say I'm having temperature is the continuous variable. So on one day I got 44.5 degrees Celsius, 30 degrees Celsius, let's say 65.6 degrees. So the values which are not whole number at all and which are in the decimal form is a continuous variable. The values which keeps on changing, a running value. So the running values are captured, and that particular variable is called a continuous variable. Okay. Now, understanding the behavior of the discrete variable and continuous variable, statistics came up with the type of distribution separately. Okay. For the discrete variable relationship, we have some distributions. We have some distribution. So one of the famous distribution is your binomial distribution. Okay. We have binomial distribution, and in continuous we have the normal distribution, or we have others as well. So if I'm tossing a coin, so coin can have either head or either tail. Okay, so if I record the outcomes of tossing the coin 10 times, then it will always come in the form of 0 1 0 1, right? But in the normal distribution, if I'm capturing the revenue of the ice cream sales, it can be like $1.6 or $2.3 or 6.9, something like that, right? That means the values which I'm capturing is a running value. So there's a difference between these two variables. And to record or to understand the distribution of such variables, we have distributions in discrete and continuous both. A binomial distribution, geometric distribution, negative binomial, hypergeometric, and Poisson distribution. So they are pretty much simple to understand. So in binomial distribution, we have x success in n events, so each with a probability p. So these are some of the formulas for the binomial distribution. Okay. So with regards to the time, we cannot discuss in depth, but yeah, you need to remember we have binomial, geometric, negative binomial just with the reverse of this one, hypergeometric, and the Poisson. Similarly, for the continuous, we have uniform distribution. So uniform distribution looks something like this. So this is a uniform distribution. Okay, from point A to point B. It looks like a constant to me. Okay, this is a constant distribution, you can say. We have a normal distribution, or you can, so normal or Gaussian, both have the same understanding. So normal distribution we have been discussing from the previous questions. So this is the normal distribution of the of any variable, and that variable is your random variable. And we have exponential distribution. So exponential looks like your exponential graph, okay, which is an exponential increment. So that's an exponential. And then we have the gamma distribution. So yeah, these are some continuous and the discrete distribution. And if you remember, there are some empirical formula like 68%, 95%, and 99.7% of the values lies within 1 standard deviation, 2 standard deviation, 3 standard deviation. So for that, you need to understand central limit theorem. We'll discuss that. Okay, so what do you understand by normal distribution? So when the mean value, when the median value, and when the mode value are equal to each other, that type of distribution is called a normal distribution. We have a symmetrical curve on the left side. We have the symmetrical curve on the right side. And if I draw a line here, then like it is going to divide your data set into two parts: 50% on left and 50% on right. This is also called a bell-shaped curve for me. Okay. and this is the asymptotic. So this is the basic definition of a normal distribution. So for any type of no, continuous variable, you should first check whether it is a normally distributed data or not. If your data is normally distributed, that means it is good to go. It is good to go for the analysis. What if the data is not normally distributed? That's a question. Okay, either your data, see, ideally I should see my data like this, okay, a bell shaped curve. What if the data is not bell shaped, it is like this, or it is like this? Now here you need to find out like why most of the data points are on the left side and why most of the data points are on the right side. Okay, so this type of distribution is called skewed distribution. Here the tail is toward the right side, here the tail is toward the left side. That's why they are called left and right skewed distribution respectively. Okay, so you need to see like why these points are more closer between this interval, or here by these the why they're the data points which are more closer between this interval. Okay, so mostly it is because of the outliers, or you can say missing value is also one of the I would say a technique, an approach to see like how much missing value my data is consist of. So missing value in our data set is always represented by NA or by just a blank cell. Okay, so and missing values generally come whenever you gather the data from the primary sources. So let's say some customer A didn't told me about the salary. Okay, so I would leave that column salary, right? And that customer told me the age. Okay, let's say 22 is the age. There's one customer who told me the salary, some number, let's say 44, let's say 44K is the salary, but this customer didn't told me the age. Now this is a missing value for the customer B, this is the missing value for the customer A. Okay, so that is our concept of the missing value, and we should always treat these missing values. And there are some techniques like we have mean imputation, we have median imputation. When I'm using the term imputation, that means I'm trying to replace this value either by mean, either by median, and it is not just limited to these imputation techniques only. We have other techniques as well. Okay, sometimes we also remove the missing values. Now missing the removing the missing values from the data set can decrease my data set size. So earlier if my data set size was 30, and if I remove these two missing values cells, that means I'm removing this customer data also and removing this customer data also, it becomes 28 cells for me, right? So here I'm losing the information. What type of information I'm losing for this customer? This customer age information I'm losing, and this customer B salary I'm removing, and that could play an important role whenever I'm computing the correlation. Okay, because maybe this customer is my regular customer in my, let's say, store, in my supermarket, right? So we have to deal with such type of uh, pre-processing techniques. Central limit theorem is again a good concept here. So basically it happens in cases when the data is not normally distributed, right? Definitely this question might have come in your mind. So I'm given a data set which is having 100 columns, not all 100 columns would be normally distributed. What if the data is not normally distributed? For such type of issues, CLT, central limit theorem, came into the picture. So when the population is not normally distributed, or it is skewed toward the left or toward the right side, but the sample is fairly large. Okay, but the samples are fairly large. When samples are fairly large, that means greater than 30. The size of the sample is greater than 30, then sampling sampling distribution sampling distribution will approach the shape of normal distribution. Okay, will approach the shape of the normal distribution. That means I got a data set. I saw it is not a normally distributed data set. What I did the sampling distribution on top of that. Now, what is sampling distribution? Fetching the samples, applying the statistical metrics, applying the statistical metrics, then computing the probability distribution. This whole process is called a sampling distribution. Okay. So on top of this data set, which is not normally distributed, I have computed a sampling distribution, which makes my data set a normally distributed. This whole process is called central limit theorem. Okay. And you need to remember this parameter. This is one of the important parameter. When the data set size is greater than 30 and the data is not normally distributed, we will perform sampling distribution to make it normally distributed. So that's your central limit theorem. And you can see from the formula, average value and the standard deviation value divided by the under root n. These are the I would say hyperparameters of central limit theorem, which will be tweaked, okay, to make your data set normally distributed. And this capital N represents that your data is a normally distributed under these parameter values. Okay, mu is the average value, the mean value of your data. Okay, another question is your long and wide format. So long and wide format is very easy to remember, because you will encounter this data whenever you do some type of analysis. So wide and long format, wide format and the long format. So I'm having, let's say, team, points, assists, and let's say rebounds. Okay, so this is the data set for me. This is the data set, and here I'm having two rows, row 1, R1 and R2. Okay, so this is B, sorry, and 88, 91 and 12, 17 and 22, 28. The data set which is having a row and having the unique value for each column. Okay, having the unique value for each column, okay, that type of data is a wide format data. Okay, is a wide format data, unique value for each column. So 28, so B team is having a rebound value of 28. Okay, A team is having a rebound value of 22. So no value is repeating here. But in long format, what happens? So again, here it is a let's say team, it's a variable and value. Okay, so A and B. So here it will be points, assists and rebound. Again, points, assists and rebound. And 88, 12, 22, 91, 17, 28. So here you can see the rows are repeating: R1, R2, R3, R4, R5, R6. Now, the important question becomes here is the size of the data. Okay, so both are having both are the same data ideally, right? I'm having the same information here, and I'm having the same information for each team here, right? But what is the difference? This is the wide format, this is the long format. Here the rows are repeating, right? For each team A, we have the repetition. So column 1, this is repeating, A is repeating 3 times, oh sorry, 2 times, and here B is also repeating 2 times, right? So this is the difference between. Now, when to use wide format and when to use long format. So every time you're going to apply some machine learning algorithms, you're always going to use wide format, because if you are going to ingest more than one row, which is a duplicate row, your machine can throw some weird results. Okay, that can show bias or maybe some variation. It will show. Okay, that cannot be a good sign when we are going to predict for a particular variable like team, points, assist and rebound. But in long format, it is going to create a problem if I'm going to apply machine learning techniques on top of that. But how I'm going to use long format? I can use it, right? If I apply a group by, if I apply a group by on a team column, then my results would be thrown separately for A team and separately for the B team. Okay. So for A team, I will get three columns. That would be a wide format only. And for B team, I would get these three columns. That means your point, assist, and rebound. And I will be getting these values. Okay. So that is the difference between your wide format and the long format. So yeah. So by default, you are going to see wide format most of the time. But if you see long format, then it depends on your objective. If you're using R, if you're using R, then for some statistical computation like ANOVA, we need some rows, because some libraries are there in R which are going to perform a separate computation on each row. Okay, which is good for a result. But again, I need to remember a use case in my mind, like whether I'm good to go with this long format or with this wide format. Okay. So that is the difference between long and wide format. So each row of the data represent the one-time information, and here the repeated responses of the subject are part of the separate columns. Here it is recognized by considering rows as groups. As I told you, I can create groups on this particular column team. A will be the group and B will be the group. And we have a direct group by function in Python, and here it is by considering column as groups. In long format, it is mostly used in R analysis to write the log files for each trial. So here each row will be a trial for me. As I told you, depends on the use case. If you're working on some use cases where each row is important for you, then it's good to have a long format. But if it is a wide format, then ideally I'm saying like it will be the best way to analyze your data descriptively and inferentially. Okay. Another important thing is univariate analysis, bivariate analysis, and multivariate analysis. So univariate analysis is just analyzing one variable at a time. Bivariate analysis, analyzing two variables at a time. And multivariate analysis basically means analyzing three variables at a time. Okay. For example, sales pie chart on the territory. So sales is one of the column. Here, scatter plot of sales with the spend volume. So there are two columns, sales and spend volume. And here multivariate, so study of the relationship between human social media habits and their self-esteem, which depends. So self-esteem is one of the column. Self-esteem is dependent on age, is dependent on status, is dependent on the relationship. Okay. So there are almost four variables which are going to be analyzed. So uni, that means only one variable at a time analysis. By that, like a bidirectional, only two direction, that means two variables at a time. And multi means multiple variable analysis at a time. Okay, what are some of the techniques used for the sampling and what are the advantages of those sampling? So your data analysis cannot be done without a sampling, because if you directly take the bunch out of the population without taking care of the values you are picking up, because see, if I'm closing my eyes and if I'm taking the sample out, then I may be missing some points which are here, which are here, which are here, right? So I need to strategically taking the sample out, right? Maybe multiple samples at a time, right? Maybe this sample which I'm taking it out, sample S1, is not having the nature of these points, right? So there should be some technique behind that. So it becomes crucial to take some data sample that cannot be used for representing the whole population and then perform analysis on it. So while doing this, it is very much necessary to carefully take samples data out of the huge data that truly represents the entire data set. Remember the example of classroom. I want to represent my class. So maybe one student is not sufficient to represent my class, right? Because let's say that particular student was good in mathematics only, right? I need one more student who is good in science subject. I need one more student who is good in social science, right? So these three students are going to represent my population or my class completely. Okay. So that type of sampling we need to do now, because I am the representative. I need to check whether I'm getting all the data points in my samples or not. Only for that we have different type of sampling techniques. So we have clustered sampling, we have simple random sampling. Simple random sampling, we are just closing our eyes and we are taking the samples out of it. So we have some random dot seed function, random dot seed function that is quite meaningful to these techniques only. We have strata sampling, stratified. We are picking the samples in the form of groups, and we are having the clustered sampling. That means I'm taking some clusters from here, some clusters from here, some from here, and some from here. And we are non-probability sampling technique like quarter sampling, which we hardly use, snowball sampling. So basically, we are using probability sampling techniques because we have to compute various distributions. Okay, we need to check that whether it is normally distributed or whether if it is a discrete variable case, I need to see whether it is a binomial distribution or not, or whether it is a Poisson distribution or not. Okay, but for our knowledge, it's good to have in our mind the like what are the different sampling techniques in the probability and in the non-probability sections. Okay, now whenever you compute any machine learning algorithm, for example, linear regression or logistic regression, or any algorithm which is going to give you a value called p-value. Okay, so p-value is nothing but just a probability value. Okay, probability value. Now what is the probability value here? Probability that an effect could have occurred by chance. Okay, it's just a normal probability value we compute, like we were computing for the dice also, and we were computing for the head and tail also. So if less than the significance level alpha, or if the test statistics is greater than the critical value, then reject the null hypothesis. Now what exactly does it mean? See, we are computing p-value in most of the departments of mathematics whenever we are learning data science. There's a term called hypothesis testing. So hypothesis testing basically is an experiment, like whether to check is it like this event is going to occur or not. Okay, is it going to be the null event, or is it going to be the opposite of null, that is your alternate event. Okay, so to decide to decide we need some factor, called alpha, that is a significance level. Okay, or some kind of threshold value, right? So if I'm saying like all those students in the class stand up whose mathematics marks is more than 40, so there will be some set of students will are going to stand. So 40 is the significance level. Okay, similarly in hypothesis testing we have significance level or some values like 0.05, 50, like 5%. So if the value is less than 5%, I'm going to reject the null hypothesis. If the value is more than 5%, I'm going to accept the null hypothesis. Okay, or it will be an alternate hypothesis case. So p-value is computed. P-value is computed on the groups of the data or on the columns. Okay, or for each feature, or I would say independent variables. Independent variables. I'm going to compute the p-value. So p-value can be computed from other methods as well. Okay, because here we are talking about the hypothesis testing, so we have one term called t statistics. So t statistics is one of the hypothesis testing tool. Okay, if I'm having multiple groups, so I'm having group 1 G1 and I'm having group 2, that is G2. Okay, and I want to compute the relationship between these two. So I have to determine the significance difference between these two groups, and that significant difference can be computed on the basis of mean, right? That means the mean value for this group G1 and the mean value for this group G2. Okay, and that should be a significant difference. Significant difference means the variables in G1 and G2 should also have the values which are acceptable, right? That should be significant to me with respect to the use cases or with respect to the objective I'm trying to meet. Okay, so we have the formula for that t statistics formula is nothing but just a mu1 minus mu2 divided by the s difference divided by under root of n. Okay, so mu1 is the average or the mean value for the G1, mu2 is the average or the mean value for the G2, and s difference is the difference between like the total number of the rows in both G1 and G2, and under root n is the total number of rows, and we are just taking the under root of that. So then in the tool, whenever you find out the results of machine learning, we will always see p value in our results, and that p value is going to decide that whether the case is accepted or whether the case is rejected. Okay. The standard cases I'm going to tell you here, which is industry acceptable here. If p value is less than 0.05, if p value is greater than 0.05, or if p value is equals to 0.05, what is going to happen? Let's see that. So if I'm having a lower p value, which means less than 0.05, that means the null hypothesis can be rejected and the data is unlikely to be true null. The null hypothesis basically means I'm saying that there is no difference. So this is the population data. I took out some sample S1. I am saying that sample S1 and population, there is no difference. That means there is null difference between them. And if I'm able to prove it, that means it is a null hypothesis case. Okay, p value. Similarly, for the p value greater than 0.05, indicate the strength in favor of the null hypothesis. It means that the data is likely will true null. See, guys, most of the cases, what happens whenever we fetch samples from the population, we always look at the very first parameter called mean, variance. Okay, and this is mu p, population mean. This is mu s, sample mean, and this is and for this we have the variance. Okay, for this we have the variance here. What exactly we're trying to explain by using the hypothesis testing, like null hypothesis and alternate hypothesis. In null hypothesis, whenever we reject it, that means there is some difference, right? There is some difference between the value of sample mean and between the value of population mean. I am rejecting the null hypothesis. The assumption was, the assumption is, the assumption is there is no difference. There is no difference between sample mean. See, I'm just taking for the example, okay? Sample mean and population mean. Okay? If I'm able to prove this assumption, because I assumed it, that there is no difference between sample mean and the population mean. But after computing by using some hypothesis testing tools like t-statistics, okay? And if there is a difference, that means I'm going to reject the null hypothesis. That's why we use p value for the purposes. Okay. So, and we have p value 0.05 means the hypothesis can go either way, either the null hypothesis case or either the alternate hypothesis case. So that is your p value. And yeah, some very steps involved in the analytics project. So understand the business problem, very important. Explore the data and become familiar with it. As I told you, like to understand the data dictionary, preparing the data set by detecting the outliers, by creating the missing values, and by transforming the variables into from one form to another form. After the data preparation, you start running the models. Okay. When your data become massaged, completely acceptable to the model, you start analyzing using machine learning algorithms, and which is basically an iterative step. Iterative step here means basically at the starting you have 50 variables. You applied machine learning algorithm. Your machine learning says from 50 variables, 40 were significant, and then you again rerun the machine learning algorithm. Now it says 30 are significant. So 30 variables are the highly significant variables with regards to your objective, which you are trying to meet. And then you validate your model with a new data set. Then because this training has been done on the training data set, now you want to see like whether your model which you have trained on the training data set is working on the testing data set or not. Okay, so it should perform the same way it is performing on the training data set, and then you start implementing using the model and using the performance over a period of time. So we have some other techniques called batch gradient descent. So These are some of the terms in between your analysis. So batch gradient descent, whenever you analyze the complete batch of the data set. Stochastic gradient descent, when you analyze one single row only. Okay, so it will be like this. So I'm having 10 rows. Okay, 1 2 3 till 10. Batch gradient descent means I'm taking the complete data set at once. This is batch gradient descent. Stochastic gradient descent, when I'm taking one single row at a time. So this is stochastic. And mini batch means when I'm taking some small crumbs of the data. Okay, let's say in the first crumb I took only 3 rows. So that is your mini batch gradient descent. Rest you are processing in your machine learning algorithms. So people might ask about these differences. We have A/B testing also. So again, A/B testing nothing but just whenever you are trying to do some randomized experiments between two variables A and B. So if A is performing at a different level, B is performing at a different level, you are trying to find out the like which is more productive to you, right? So the goal of A/B testing is to identify any changes to the web page to maximize or increase the outcome of the interest. That outcome of interest depends on the technique you are using, either the technique A, either the technique B, or some other technique which you are trying to find out. An example of this could be determining the click-through rate for a banner ad. Okay, so whether I'm going to click on the banner, if I'm clicking on the banner, whether I'm proceeding further or not. Okay, so I have to test it out. So this is a randomized experiment. Okay, to find out the best approach. So again, this is a statistical hypothesis testing. And how will you calculate the accuracy of the model using a confusion matrix? So accuracy of the model for the classification models, we have confusion matrix. Okay, we have confusion matrix. We have true positive, we have true negative, we have false positive, we have false negative. If I'm going to take the sum of true positive and true negative divided by true positive plus true negative plus false positive plus false negative. That is your accuracy of the classification model. Okay. And you can build confusion matrix. You can build a confusion matrix for any classification model. There are direct functions for that. You just need to import. So this is the positive, negative, positive, negative. So on one side we have the actual values, and on another side we have the predicted values. So basically it says this is the actual value and this is the predicted value. So with an example, I would explain here. Let's say let's say 3, 2, and 0 and 1, and these are the actual, and this is the predicted one. Okay, 1 0 1 0. So here it says the three values model has identified as the actual value and they are predicted as well. Okay, three values who are actually who are actually like good in the actual data set were predicted correctly by the model. Okay, similarly for the value 1, the value which was 1 in the actual data set, the same model has predicted for me. Okay, that is the predicted. Where the error comes here in this case, if you see this 2, here the model says that in my actual data set 2 data point belongs to, let's say, A category, but my model is saying no, it is not belonging to A category, it is belonging to B category. So here is an error. Similarly for this case as well, here the model says that let me make it 10 because I won't be able to explain with that. So 10 points has been identified belonging to the 0 category in actual data set, but my model is saying no, they are not belonging to 0 category, they are belonging to the 1 category here. Okay, so that is an error. That is an error in my classification model. So we always try to minimize false positive and false negative. Mostly false positive. We always focus on false positive. We have to minimize it to make our model more productive, more efficient, so that we can push this model into the production to capture as much as true positive and true negative rates. So machine learning we have already discussed, and supervised and unsupervised also, and bias and variance trade-off. So bias and variance trade-off, a quite snapshot about this will be like, so for example, you have some data set. Okay, you have some data set. You have divided the data set into two parts: training data set and testing data set. Okay, you applied some pre-processing techniques, so you make your data more. So this is your 70%, let's say. Then this is your 30% testing data set. So on top of 70% data set, you applied some machine learning algorithm. It performed well for you, right? For example, and now what you have to do, you just need to test your model on the 30% data set. That means you have to evaluate a model on the testing data set. Evaluate on testing data. What if your model performs completely different? Okay, so on 70% data set, I was achieving the accuracy of 98%, and on testing data set, I'm achieving the accuracy of 58%. There's a huge difference between these two accuracies, almost a loss of 40%, right? So that type of issue will always occur. That's why the concept of overfitting and underfitting comes into the picture. Okay, overfitting and underfitting. You should always train your model on the training data set, and the model should not see the testing data set. Okay, if it sees the testing data set, that means you have already ingested while processing into machine learning algorithm. Okay, so overfitting is one of the issue which we face in our day-to-day life. So we, to overcome the overfitting, we introduce the concept of bias and variance trade-off. Bias and variance trade-off. Basically, what we do here, we have some techniques like regularization. So we add some bias. We add some bias to overcome the overfitting here. Let's study that. So bias is an error introduced in your model due to oversimplification of the machine learning algorithm. It can lead to underfitting or overfitting as well. When you train your model at the time, model makes simplified assumptions to make the target function easier to understand. So we have some standard results. So low bias machine learning algorithms, we have like decision trees, KNN algorithm, support vector machine. For high bias, we have linear regression, logistic regression. So high bias, I would explain in a way. So if I'm using linear regression, I'm expected to see the results like this. Okay, let's say this is the predicted model. This is the predicted model, and this is the actual. This is actual, and this is predicted. Okay, so there's a difference between. There's a difference. This is called error. Okay, what if I'm using a polynomial regression? So polynomial regression, let's say this is the line, and this is also the predicted line. This is also the predicted line, almost capturing all the data point. In this case, you will see a lot of errors because this model, which was trained on 70% of the data set, cannot perform well on the 30% data set because this is overfitted on each point. Okay, but in this case, this can be generalized. This can be generalized. Okay, it can at least give me some generalization on the testing data set, but it won't give. That's why the bias and variance trade-off has to come into the picture. In this case, variation will be there. In this case, variation will be there. That is low or high. That depends on the data set. So variance is also the same thing. So it can lead to high sensitivity and overfitting. Normally, as you increase the complexity of your model, you will see a reduction in error due to lower bias in the model. So they have their own understanding. Whenever you study your machine learning concepts, you need to check, are you getting the same results on the testing data set or not? And again, why resampling is done? Again, to avoid the problem of not capturing the right data point, right? That's why resampling is done. So estimating the accuracy of the sample statistics by using the subsets, which we have already discussed. Differences of overfitting and underfitting, which we just use. So this is the example of your a negative correlation, right? And this is the example of a polynomial. So like when you train the model, your 70% data set has been captured on this curve, but when it comes to the testing data set, it is not predicting at all. So that is the type of the problem you will see. This is overfitting and this is underfitting. So there is no relationship you can see between the cross sign and between the circular symbols, right? So these are some of the definitions. So see, you can never learn these definitions by heart, and it's not required at all. You will always try to understand these concepts by experimenting on your own. So it's very important. Otherwise, you will always forget to answer these questions during an interview. So yeah, as I told you, regularization is one of the technique. So L1 technique is there, L2 technique is there. So lasso regression, ridge regression. So they are nothing but just the bias values. Okay, bias is being added. So in a layman language, it's like this. Um, okay, so we have, let's say, y is equals to mx plus c is the let's say a linear regression equation. Okay, if I add L1, depends on the use case, whether you are facing the high bias or whether you are facing the low bias. Okay, so depends on the use case. So L1 and L2 are being used according to that only. Okay, so L1 is the regularization which is being added as a bias to your linear regression algorithm. That's why regularization is important. It is not only just limited to machine learning, it is highly used in deep learning also. When you are like whenever you are writing the optimization equation for neural networks in artificial neural network, you highly use L1 and L2 regularization a lot. Okay, to again to have a good trade-off between your bias and variance. Let me have that chart here. Should be here. Okay. And again, there's a good question about how an ROC curve being used in classification algorithms. Like we have confusion matrix, we have ROC curve as well. It is a graphical representation to show the contrast between your true positive rate, that is a TPR, and false positive rate at various thresholds. So this question is being asked to me as well. So the question was like, what will be the threshold value? What will be the threshold value you and like I'm going to decide using ROC curve, because ROC curve is your TPR versus FPR. Okay, that you can see here. TPR versus FPR. Your TPR is on your y-axis and FPR is on your x-axis. So I need to find out the best threshold value. That threshold value can be here, can be here, it can be here. That threshold value is the value which is going to decide, because we are classifying this, right? Let's say I'm classifying male and female on the basis of, let's say on the basis of education, who are more educated, right? So I need to find out this barrier value. Okay, on the education parameter. Okay, so that threshold value is being tested from this curve. You can see from 0.2, 0.4, 0.6, and 0.8. So these are some of the threshold values. And just below that we have AUC also, area under the curve. So we would always want all the data points to come under this curve. Okay, area under the curve. That will like if you're getting 90% as an AUC value, that means it's good. 90% of the data points you have captured completely. Okay, but still 10% are there. So always try to change the threshold value to make your AUC more efficient. And then we have PCA. So PCA, guys, is one of the best technique to have the more basically is going to decrease the size of the data set. PCA. So I'm having around, let's say, 5,000 columns. 5,000 columns. Can you imagine 5,000 columns? And those 5,000 columns you cannot process at one go, right? So you need to find out the all those columns which are related to your use case, or which are related to your problem statement, your business problem, right? So we apply some PCA technique, that is a principal component analysis. Okay, we have LDA also for the same task. So what PCA do, it tries to minimize or decrease the size of the features, decrease the data set, I would say here. So from 5,000, let's say 1,000 were the good one, over 1,000 were the one who are actually required for the machine learning process. to resolve your business problem. Okay, so PCA is the technique. So basically we are losing the data set, right? From 5000 to 1000 column, we have lost around 4000 of columns which are not related at all with respect to my business problem. So for that we have this technique. Okay, so standardize. So we have the process to apply PCA, standardize the data points. That means compute the standard normal variate for each data point, find the covariance matrix, carry out the eigenvalue decomposition, and sort the eigenvalues. You don't need to do all these steps. It's just for the understanding. Your algorithm is going to do it for you. Dimensionary reduction with PCA. So 5000 column means 5000 dimensions. Let me make it clear here, 5000 dimensions. And if I'm applying PCA and making it just 500 dimensions, so that is the reduction of the dimension using the PCA technique. That means 500 are the most significant one which I'm going to use for my machine learning process. So that is your PCA. And we have regression analysis. So regression analysis, whenever we are trying to fit our algorithm, okay, with respect to the linear regression line, which is your yi is equals to fxi, that is your y is equals to mx plus c. This is your straight line equation. Okay, and that straight line equation can be easily converted into a regression equation. So if I'm having a target variable y with beta naught as the constant value, which is c intercept in your linear regression line, plus beta 1 x1 plus beta 2 x2 and so on. So beta 1 is the correlation coefficient for or you can say not correlation coefficient, it's just the coefficient for this variable x1. This is the coefficient for the variable x2. Okay, so this is the linear regression line. And regression analysis says if I'm trying to fit this line on this curve, it should always show some type of relationship, and that to be a increasing relationship. Okay, so linear regression, we have logistic regression, and we have other regressions too, like Bayesian regression, ridge regression for our analysis. And during the regression analysis, we have some evaluation parameters like the sum of the squared method, like a mean absolute percentage error, like a mean absolute percentage calculation, and other techniques too, to find out like whether your model is behaving perfectly or not. We have R square metrics. We have adjusted R square. So in regression analysis, all these terms comes under. And you can see linear regression, a straight line relationship. Polynomial regression, it tries to fit all the curve on the points, like all the data points you can see on the line. In Bayesian regression, there is a weird pictorial graph you can see, right? So Bayesian linear regression sometimes may not fit according to the data. Okay, logistic regression is the S-shaped curve, because logistic regression is the classification algorithm. So most of the data points are close to 1, and most of the data points are close to 0. Okay, so that's why it is trying to form the S-shaped curve. It cannot be a linear regression curve here, because it won't be able to capture all the data points at 0 and at 1, as they are categorical variables. And the fit statement for linear, polynomial, Bayesian, ridge, lasso, logistic, it's very important here to remember this. So we have some estimated functions for linear, polynomial, Bayesian, and for all, and these are the error functions. So error function basically always, like, our concern as a data scientist is always trying to minimize the error, right? It is very important to minimize the error for each algorithm, whatever we are using. So if I'm getting some error using this, we have to do something, or we have to pre-process the data, and we have to find out some variables who are responsible to create this error. Okay, so, and these are the estimated functions, or you can say the regression line, which I just wrote it here. Okay, so again, I think this question is repeated. um, yeah, there's a question: if the training loss of a model is high and almost equal to the validation loss, what does it mean? This is our production level question actually. If the training loss of a model is high, that means on the training data set your loss value is very high, and almost equal to the validation loss. What does it mean? So you need to understand, are you like doing the iterative modeling like epochs? So epochs are nothing but just the steps. Steps walked through each data point. Epochs are nothing but just steps. Okay, so if I'm having 3 rows, so my model is iterative model, right? So it is going to visit this also, visit this also, visit this also, and then it is going to compute the loss value. Okay, so what it is just trying to say, if the training loss is much higher than the validation loss, or if the training loss is almost equal to the validation loss, it means that your model is underfitting. Okay, or in other words, your model is not complex enough to properly understand the underlying relationship between the dependent and independent variables. So it could be because of lack of data also, lack of data, because it is not trying to establish the relationship between the variables. Okay, so train your model longer for more epochs. That means ask your machine learning model to understand or to visit these entries more, like for the longer time, to capture all the weights. So we have the weights computed for each step. Choosing a more complex learning model than the current one. It could be the technique to overcome the underfitting, or creating the new features which are non-linear combinations of the previous. So this is the transformation of a variable here, and performing data augmentation if possible. So data augmentation means you are augmenting the data. Augmenting means you are adding more features to the data. Okay, you are adding more features. You are basically trying to increase the size of the data. Okay, increase the size of the data. So if I'm having a picture here, let's say this is a smiley picture here, and I want to augment this image. So this image can be like this as well. This image can be like this, and this image can be like this, or this image can be like this. So we are augmenting. I just augmented this image into another 5 images. So I increase the data set. So maybe by increasing the features, your underfitting can be overcome. So these are some techniques. And to overcome the overfitting, we have simplifying the models using the regularization techniques like L1 and L2. Augmentation can be helpful here as well. And early stopping of the model. That means if you are not training your model for longer period, if you're training a model for longer period, that means you are overfitting it. Okay, you're trying to overfit, or you're trying to overcome the values which your model has trained at the early stage. So early stopping is the technique to find out the optimal value, the optimal value of epoch, optimal value of epoch here. Okay, if you're able to trying to find out the best value of epoch, that means it is a more generalized model. Let's say I trained my model 5 times and it is giving me the good accuracy, so 5 is the optimal value here. And then we have the dropouts, and then we have the feature reduction. So again, feature reduction is your PCA technique, and dropout means if you're working on the artificial neural networks, you can drop out some hidden layers in between them. Yeah, so to find out the, so in k-means clustering, so basically guys, there is a concept called elbow screen method. So k-means clustering we cannot discuss because it's a slightly bigger algorithm to discuss at this platform right now. But yeah, people used to ask like what is the right k value. So to find out the optimal value of k, like we used to compute the optimal value of epochs in deep learning, we have the elbow screen method or silhouette is measure method. Okay, so elbow screen method basically, in a pictorial picture I would create here is like this. So elbow screen method, you just have to find out the best point here. Okay, that point, that particular coordinate is your elbow screen method recommendation, that take this value because the way it just become bent or just become parallel to your x-axis, that particular edge point is your k value. Okay, so let's say the k value here was 3, so k is equals to 3 is my optimal value to be used in k means clustering. Okay, that means 3 clusters are going to be formed. That means 3 clusters. And what is the importance of having a selection bias? So selection bias when no appropriate randomization is achieved while selecting individual groups or data to be analyzed. Selection implies that obtained sample does not exactly represent the population that was intended to be interpreted. Means when you are finding out the samples, okay, So maybe you're selecting the individuals, or maybe you're selecting the groups or the data that you are going to analyze. So you are introducing a bias, okay, from your own. That means I want to select only those students who are good in maths. That is the bias which I'm introducing from my side. Okay. So sometimes it is useful, but in general it is not a good technique. But yeah, it is a good technique to have a more refined results. So selection bias consists of sampling bias, data, attributes, and time interval. Why data cleaning plays a vital role? I think we have already discussed, because we are cleaning the data by treating the missing values, by detecting the outliers in our data set, or by detecting the negative values also. If you are having negative values in your data set, then you need to check your data dictionary, because sometimes the outstanding in your credit card bill is a negative, and that makes sense, right? So that negative value is making sense here. But if you're having minus $33 in the salary column, that doesn't make sense. So treating the negative values, treating the missing values, detecting the outliers are some of the data cleansing techniques. So that is your vital role for the analysis. And most of your, not just 80%, your 90% time goes in data cleaning only. Because once you clean your data according to your needs, you are good to go with the machine learning algorithm to be built on top of that. And what are the recommended systems? So if you have heard about the Kafka systems, the recommended system, which Amazon is also using and other companies as well, is basically the subclass of information filtering system meant to be predict the preferences or rating that a user would give to a product. Like Amazon is showing like the products where, like if you're buying a fridge, then might be Amazon might be selling you the fridge cover as well. Okay, whenever you check out from the instance, it will so like it is being recommended to buy this cover for your fridge, like that. So that is the best example of a recommender system. It is kind of a collaborative filtering here. So the process of filtering is used most of the recommender system to find out the patterns or information by collaborating viewpoints, various data sources, and multiple agents. Basically what it says, it is trying to find out the hidden patterns. So what Amazon is doing, it is trying to find out the hidden patterns from where, from the historical data. From the historical data, it detected some pattern that people who are buying fridge, they are buying the covers also. Okay, they are buying covers also. So let's try to recommend the same thing to our new buyers. Okay, so that is the basic functionality of your recommender system. So this is all about your question and answer sessions. And just try to make your own notes and learn the basics of statistics, probability, machine learning with examples. It's good to understand, because it's very hard to remember the definitions. Okay, so thank you so much everyone, and yeah, all the best for your interviews.